What if I told you an AI can learn to master a game from zero knowledge just by playing it over and over again? No rules, no strategies, just trial, error, and math. Welcome to the world of reinforcement learning. At the heart of this process is a loop. The AI or agent observes the environment, let's say a game screen, makes a decision, takes an action, and gets feedback, called a reward. This loop repeats again and again. Over time, the AI learns good actions lead to good outcomes. This learning process is called reinforcement learning. It's inspired by behavioral psychology, the same way dogs learn tricks with treats. The agent's goal? Maximize the total reward over time. But how does it actually learn what actions are best? Mathematically, Q-learning updates its values using a key equation. The Q value for a given state in action is equal to the reward received plus gamma times the maximum Q value for the next state in all possible future actions. More formally, we write this as Q of S and A equals R plus gamma times the maximum Q of S prime and A prime. Here's what each term means. S is the current state, the situation the agent is in now. A is the action the agent chooses to take. R is the reward it receives after taking that action. S prime is the new state the agent ends up in. Gamma is the discount factor, a number between 0 and 1 that controls how much the agent values future rewards compared to immediate ones. And the max of Q of S prime and A prime means the agent looks ahead and assumes it will take the best possible future action from the new state. In simple terms, each Q value gets nudged toward a new estimate, the immediate reward, plus the best the agent can hope to earn afterward. Over time, this process allows the agent to discover better strategies and eventually converge on the optimal one. In simple games, we can store all Q values in a table. But in complex games, like Atari or 3D environments, we use a neural network to approximate the Q function. This is called a deep Q network, or DQN. The input? The raw pixels from the screen. The output? A list of Q values for each possible action. But if the AI always chooses what it thinks is best, it might miss better options. This is the exploration versus exploitation dilemma. The agent sometimes needs to try something new, even if it seems bad, to discover better paths. This is often handled with an epsilon greedy strategy. Explore randomly some of the time. Let's put it all together. In 2015, DeepMind trained an AI to play Atari Pong using deep Q learning. At first, it misses every shot, but after millions of games, it starts to understand the physics. Eventually, it plays better than any human. No instructions, just rewards and experience. These methods work astonishingly well in virtual environments, but they're not perfect. Real-world learning is much harder. Environments are noisy, complex, and expensive to experiment in. That's why many researchers combine reinforcement learning with other techniques like imitation learning, curriculum learning, or even large language models. AI learning to play games isn't just fun. It's a gateway into how intelligent agents might learn anything, from driving cars to solving scientific problems, all starting from nothing and learning through experience. If you enjoyed this breakdown, don't forget to like, subscribe, and dive deeper into the next episode.